Alright, let's get started with this lecture video, Lesson 3, Bond Enthalpies. Alright, to start out with talking about bond enthalpies, I want to review some background information. Remember that the process in breaking a chemical bond is endothermic. That is, energy is required to break chemical bonds. Now, the bond enthalpy is the energy needed to break 1 mole of bonds in gaseous molecules under standard conditions. Now, this definition of bond enthalpies is very important, and I will expect that you will learn this definition of what bond enthalpy is. So again, I'm going to underline or highlight this. Bond enthalpy is the energy needed to break 1 mole of bonds in the gaseous molecules under standard conditions. Now, we'll explain what standard conditions are in the next lecture video, as well as we'll point them out in class. But for now, just make sure you understand that bond enthalpies take place under standard conditions. Also, it is important to learn this definition of bond enthalpy, which I mentioned, but a common error in the definition is that a lot of students fail to indicate that all species have to be in the gaseous state. Alright? So from this idea we can take away is just bond enthalpies is the amount of energy needed to break chemical bonds. Alright, so we have a table here in your notes that lists the bond enthalpies of specific types of bonds. So if you look at, for instance, a CH bond, here this is the first one, a CH bond, it requires 413 kilojoules of energy per mole of CH bonds to break those bonds. You can see with a nitrogen-hydrogen single bond, it requires 391 kilojoules of energy. So anyway, this is a nice table that lists the bond enthalpies, or the energy required to break, the amount of energy required to break these chemical bonds. You will not be required to memorize these values, but you should be able to use these values in various calculations that we'll do, as well as recognize that these values are the energy required to break chemical bonds. Right? The other thing I do want to point out in this is more or less something that you should know and learn is that double bonds and triple bonds and single bonds require different amounts of energy to be broken. So if you look down here at the carbon-carbon triple bond here, highlight that, it takes 839 kilojoules of energy to break it. But right above it, the carbon-carbon double bond only takes 614 kilojoules of energy. What does that mean? Well, that just simply means that double bonds require less energy than triple bonds to break. So therefore, triple bonds are much stronger than double bonds. Triple bonds are stable. They have very low potential energy, so it requires a lot more energy to break those triple bonds. Whereas double bonds, they're not as stable. They have a higher amounts of potential energy, so it requires less energy to break triple bonds. And then if you look at the carbon-carbon single bond, it only requires 348 kilojoules of energy. So what we're saying is, in terms of bond strength, is that triple bonds are the strongest, then double, and then finally single bonds. And you need to basically understand this generalization about bond strength between triple, double, and single bonds, and relatively how much energy it would take to break these bonds. Alright? Alright, so now that we've looked over this bond enthalpy table, let's add a little bit more information here. So if you recall that during an exothermic process, bonds are going to be made. When bonds are made, energy is going to be released, and so therefore it must be exothermic. So energy is released when bonds are formed, and that's something we've spent some time talking about. The same amount of energy, and this is pretty important. So the same amount of energy required to break a bond is also released when a bond is formed. So these values in the table above, so for instance our carbon-carbon double bond, that energy is 614 kilojoules. That's the energy required to break that bond, but it is also the exact same value that is released when a carbon-carbon double bond is formed. Same thing with this nitrogen double bond. It takes 418 kilojoules of energy to break the bond, but we also release that amount when we form a double bond between two nitrogen atoms. The only difference is the sign. Alright, these are all positive signs because it takes energy to break bonds, so they're all endothermic. But when we release energy, or these values, and we just have to change the sign to a negative, indicating that energy is being released when we form these bonds. Alright, so that's a pretty important relationship to understand. Now, bond making involves bringing together atoms, right, which are attracted by electrostatic attractions. And this then overall decreases the enthalpy of the reaction. And this is kind of what we've been dealing with throughout this unit on thermodynamics, is understanding that when atoms come together, they're attracted by electrostatic forces. The stronger the electrostatic forces, the lower the potential energy. And so again, with triple bonds, they have very strong electrostatic attraction, so therefore they have lower potential energy than like double or single bonds. And so the overall enthalpy of the reaction should lower here. Alright, now where can we use these bond enthalpies? Well, we know that calorimetry is an excellent way and for us to actually determine, the amount of enthalpy change in a reaction. Now let's remember that enthalpy change is really the change in potential energy of the system, as long as it's under the right conditions, which we've talked about. So we can use bond enthalpies to actually calculate the overall change in potential energy, or the change in enthalpy of a reaction. And that can be done by using this equation right here that I'm going to highlight. And that is the enthalpy change of a reaction, and the little knot up there, that little circle there, that means this reaction is taking place under standard conditions. And so we'll talk about this little knot right there later on. Alright, so it just says simply the change of the enthalpy of the reaction at standard conditions is equal to a funny looking sign here. This funny looking sign that I'll point out right there is called a sigma. And what sigma means is the sum of. Alright, so we're basically going to take the sum of the energy required to break chemical bonds, and we're going to subtract that by the total sum of energy required that is released when a bond is formed. So essentially in this equation, to find the overall enthalpy change of a reaction, is we're going to take the sum of the bonds broken minus the sum of the energy of the bonds release, or the energy that's released when a bond is formed. And if you can use this equation and memorize it, this can have some quite value to you, or should. Alright, so what we're going to do is we're going to use this equation for some practice problems here. And we're not going to go through all of them. We'll do a few, and we'll do some of these in class to make sure and double check that we're okay. But let's go through at least 2 or 3 of them. Alright, so it says calculate the enthalpy change for these reactions using bond enthalpies. So what we're going to have to do is we're going to have to use the table that I provided in your notes in order to determine the bond enthalpies and calculate these. Okay, so I'm going to go to a whiteboard here that we're going to do number A first. So this is going to be letter, let's change that to letter A here. Alright, now I think the most important thing you can do to start out with bond enthalpies is to actually write the Lewis dot structures for each of the substances, the reactants and products that are in the reaction. This is going to help a lot. So in A, it says if you look at the reaction, we have to break a hydrogen, H2O, and a chlorine, Cl2, which is a single bond, and that produces HCl, which is a single bond there too. So there's the Lewis structures. So essentially we're going to have to break this bond. We're going to have to break this bond. Alright? And so we're doing the bonds broken minus the bonds formed. So the delta H of the reaction at standard conditions is equal to, so look at your table, how much does it take to break the HH bond, a single bond, and you would find that it takes 436 joules per mole of energy, right? Now we're going to add that amount to the amount of bond or amount of energy that's required to break that that single bond between the two Cl's. And if you look at the table, that is 242 joules of energy. Now that's the number of bonds that are going to be broken, and we add those together, that would be the total amount of energy required to break all bonds in the reactants. Now we're going to subtract this from the amount of energy of bonds being formed. So we're only going to form one bond, this single bond between the hydrogen and the chlorine, and it requires 431 kilojoules of energy to be released when we do so. So if we add our bonds broken and subtract it from the bonds formed, we should get a delta H of reaction value of, let's see here, do a quick calculation. Alright, I just looked at back at the equation. I realized we did one thing wrong. We're actually, let me erase this, because we're actually forming 2 of these. So we're actually forming 2 Cl molecules. So we actually have 2 of those. So that means we're making 2 of these bonds. So we have to multiply it 2 by 431. There, that will fix it. So when we do that, and we add and we multiply and subtract and all that good stuff, we should get a negative 184 kilojoules per mole. And that should be our answer to A. Alright? Okay, so let's go ahead and do B now. So I'm going to erase this. And let's look over B. Alright, so in B, it looks like we have 2 hydrogens. So again, we're going to draw the Lewis structures. So we have 2 H2s, and they're going to react with oxygen, which is a double bond, and we're going to form 2 waters. And another water here. Okay, so we're forming 2 waters. Redo that bond a little bit. Alright, so that means we have to break these 2 bonds, and that's going to require 436 kilojoules, and we got to multiply that by 2 since we have 2 of those. Plus, we have to break that bond, which if you look at your table requires 495 joules per mole. Okay, so that's our bonds broken. Now we're going to subtract that from the bonds formed. Now we're going to form 4, let's count them, 1, 2, 3, 4 single OH bonds. And so we're going to multiply 4 bonds by 463. That's the amount of energy that will be released. And so then we do the multiplication and addition and subtraction, and we would find that the delta H of this reaction is equal to negative 485 kilojoules per mole. Alright? At standard conditions. Alright, so that should be the answer to B. Alright, go ahead and make sure and double check the math and everything. Alright, so there is 2 example problems on how to do this, and I think maybe we should go ahead and quit here on this video. Time is running on here. What I would suggest is that the other 3 problems, C, D, and E, try to work those out on your own in your notes. Use your table that is provided in your notes and see if you can actually calculate the change in enthalpy for those 3 reactions, C, D, and E. Alright, that is all for this lecture.